like waiting for you guys to say something and then I'm like mic'd up to the dean going, I got him. No, they admitted they hate it. If it makes you guys feel any better, that's how I feel some Fridays. That's how I've got some stuff I got to catch up on for the end of the block. And this week was killing me as far as getting everything in and getting the quiz up and doing stuff. And oh yeah, it turns out I have 3 children in 3 different school districts. Then they still have homework. No matter how far ahead I get on my homework, they still have homework to do. And it should sound like they're in elementary school, middle school, and high school, and you would think, oh, well, you teach college math, that should be easy. But in a weird way, it's too far behind, and so then I have to like reinstall the geometry or the trig libraries back into my brain, because I've been doing 356 so much that if my son wanted to know, hey, how do I do a p-test, or how do I do a binomial distribution, I'd be all over it. But when he comes up to me and goes, hey, can you tell me how would I figure out what angles X and Y are in this parallelogram? I'm just like, are you sure you don't want to just do like a negative binomial or a Poisson distribution? Maybe we could turn that in and your teacher would be just as happy. Plus, I don't get to teach it the way I want, because they will show me stuff and I go, well, I know how I would do it, but how did your teacher teach? And they're like, well, no, just show me how to do it. And I was like, no, because I'm going to piss your teacher off if like you turn this in and it has, integrals and derivatives on it. And she's going to be like, what is, or she's probably just going to be like, your dad's a teacher, isn't he? Mm-hmm. All right, well, I'm going to give you an A, and then I'll have a parent-teacher conference with him later. I try to be a good dad and teacher and fight the urge to. I've only once so far in one of my daughter's papers told her she didn't have to do it, and then I wrote at the bottom of it, I told my daughter not to do this problem. It is a bad problem and will make her understand the subject less. Signed, Dr. Richards. Which they hate when I do that, which is great because then they just do more of their homework on their own. Okay, we are 2 minutes in, and so I should get to teaching because we went over on first period, and just because they're a lost cause doesn't mean we can't still save you guys. Not only is it the end of a week, it is a true end of a week because it is the end of a block pretty much. We have lessons 11 and 12, or 12 and 13 next week, but today is the last day for any new material. Next Tuesday is a review day, and next Thursday is the GR. So what that means is Tuesday we're doing review. I'm not going to plan a lesson per se. It's going to be all for you guys. Between now and Tuesday, just shoot me messages. I'll put out some more messages on this. But anything you want to see, whether it's like, hey, here's a question from the homework, or here's a question from the book, or here's a question from a quiz, or here's just a question I had, and we can either work them out completely, or if they're just conceptual, we can answer them. But that's what Tuesday is going to be, is led by you guys. If you guys all come in and no one has any questions, and you go and you say, yeah, we feel pretty good, I'll probably let you guys go early and go, awesome, A's for everyone then on the GR, I guess, and you guys can leave. With respect to the GR, we can talk more about this as well later, but it is next Thursday. Like the quiz, you will have that 2-day window to decide when to jump online and take the GR, because the GR is going to be online the same way the quiz was. Unlike the GR, we are not meeting for class on Thursday. Because the GR takes more time online, it would be a jerk move if I said, you need to find your own time to take it and still come to class. So we will not be meeting for class on Thursday. And then sometime on that M day or the following T day, you find the time to get online and take it. Like the quiz, once you start, you got to finish it. So make sure you block off that time that you can do it. Along with that, that means that if you've got questions or EIs or anything like that, bring them to the review, but get them answered by Wednesday, because I'm going to have myself and all the instructors institute a EI blackout Thursday and Friday when the GR is live, because everyone's going to be taking the GR. So I don't want people doing EI, because for all I know, you have the test open and you're saying, yeah, okay, here's another example of a question. What if the question was this? How would you answer that? Right, which luckily none of you are that dirtbaggy and none of my instructors are so stupid that they would fall for that. But we're still not going to do it just so we can all maintain an easy academic integrity there. So make sure you get your questions in before the quiz or the GR opens on Thursday morning. Okay, any admin questions that you guys have on stuff that was due this week or is coming up due next week or just things that are happening in general? Awesome. Okay, so today we are going to finish off on our adventure into the world of discrete random variables, right? Oh, I just realized that I thought I was sharing my screen this entire time, but I'm just looking at it. So let's share it. There we go. Now we're all literally on the same page. That's great. So yesterday, not yesterday, Wednesday, you know what I mean? Yesterday in the world of us seeing each other. I don't count days that I don't see you guys. They're empty and meaningless to me. So as far as I'm concerned, Wednesday was yesterday. We introduced two discrete random variables, the geometric random variable and the binomial random variable, right? And both of them were versions of summing up a Bernoulli, right? A Bernoulli trial or random variable is just a thing where you do it and it either succeeds or fails, 0 or 1. You flip a coin, heads or tails, right? Geometric says if I do that thing that succeeds or fails over and over and over again, a geometric random variable is a random variable that tells me how many trials did it take for me to get a success, right? So if a geometric random variable x is equal to 8, that means I did not succeed. I did not get my first success until my 8th try. A binomial random variable says, hey, do that coin flip or that succeed fail thing over and over and over again a set number of times, n times, and then count how many times you succeeded. And that's the binomial random variable x. So if a binomial random variable x is equal to 5 for a n of 100, that means I did the thing 100 times and I succeeded 5 times out of that 100, right? So that is the general explanation of what a geometric and a random variable is. And then we talked about how I would do different things in the code for that. Any questions in general about geometric or binomial random variables that are still bugging you guys? Okay. So we talked about how we do the different functions on that. We can look more at that later or on Tuesday or later today if you want. And then we looked at these questions. And correct me if I'm wrong, because different sections did things a little differently. If my understanding is yesterday, I think we were able to work through questions 1 and 2, but I left 3 to you guys to look at. Is that true? If you guys are nodding, I can't see you. I need someone to say yes, no, maybe so. It's going to make me ask someone specifically. Simon, is that what we did?
Sir, the only thing I heard from the last 3 minutes is my name.
Nice. Okay, is that because I'm jumping in and out on the network, or because you're playing Fortnite in the background? So my question was, did we go over questions 1 and 2 in class on Wednesday and leave 3 for you guys to look at it? I couldn't remember who did, if I did that in this section or the other section.
Sir, I don't know if he can hear you. I'm pretty sure that's what we did. I don't have the best memory, but I'm pretty sure that's what we did.
All right. So am I getting? Am I tripping in and out here in general? Are you guys having like if you guys are if there's some connection issues, you guys got to let me know because I don't. While I love the sound of my own voice, I would feel bad if I was spending 15 minutes talking and no one was hearing any of it.
I mean, you're not completely like breaking out for me, so like I hear full sentences, so
Okay. What about, let me just do some random checks. Preston, are you hearing me?
Yes, sir.
Grace, how about you? Is it all coming through?
Yes, sir. It's going in and out, but I think it's on my end.
Okay, yeah. My apologies for those of you who lost the dorm lottery and got a place that has absolutely network connection. I can only do so much about that. But if it is a problem, let me know because I don't want to actually affect what you're being able to hear here. So let me pose this question. I'm telling you, what I'm going to do is I think we talked about going over 3. I'm going to skip to the next slide and I'm going to talk about the last 2 distributions we have. But then if you guys are interested, I am still happy to work through this problem. So let's look at the new material and then we will come back and look at a review altogether if that sounds good. So we're going to introduce the last 2 discrete random variables. So at the end of this, you are going to have 4 different discrete random variables that I can ask you about, and 1 continuous, right? So we've only learned 1 specific continuous random variable, the normal distribution, and then you guys have learned 4 discrete random variable distributions: the geometric, the binomial, and then the 2 I'm going to teach you today, right? And I say that because those are the only 5 named distributions that I am holding you guys responsible for the GR. So when I ask you something of what distribution should you use or anything like that, those are your 5 named options. So those are the ones that you need to be able to understand and differentiate. So the negative binomial random variable is like the binomial random variable. So we just finished talking about the binomial random variable. The binomial random variable says, I do a thing a set number of times. And then the binomial random variable counts how many successes I got. So I flip a coin 100 times. And then the binomial random variable says, how many times did I succeed out of that 100, right? The negative binomial random variable, the reason it's the negative or opposite is that it's a similar situation, but instead of setting how many times I do a thing, it sets how many times I succeed. So the negative binomial random variable says, I want to succeed 10 times. And then the random variable counts how many trials does it take until I get 10 successes, right? So binomial random variable, I do it n times, and the random variable counts how many times I succeeded. The negative random variable sets how many times I have to succeed, and the negative binomial random variable then counts how many times did it take for me to succeed that many times, how many times until I got my kth success. So we'll go into the math of this in a little bit, but does the concept or the scenario of a negative binomial random variable make sense? Any questions on what a negative binomial random variable represents? Questions on that, or just explain it again, or give an example, or something like that? Okay. And we'll get into the R code of how to do it, but we'll go on to the last variable and then we'll do it all together. The last one is called the Poisson random variable, which is named after a guy. If you speak French, it is not named after fish. It's named after a guy who the guy was probably named after fish. But a Poisson random variable is it's a special random variable that counts how many times something happens over an interval. And the important thing to understand is that interval can be a lot of different things. A lot of times it is time, right? So if I say, hey, let's use the example of what we're dealing with today. Let's say that MissionNet fails according to a Poisson distribution, right? So then X would be the number of times MissionNet fails in a particular interval. Like, how many times does it fail in an hour? Or how many times does it fail in a day? Or how many times does it fail in a semester, right? So that's what the Poisson random variable represents. It's the number of times a thing happens over an interval, right? But it doesn't always have to be time. It could be something like, I think I used an example later of trees. Let's say I have a ranch and trees grow randomly, right? And so I could talk about the number of trees on an acre of land, right? That's a random variable because from 1 acre to another, I have a different number of trees, but they're distributed according to this Poisson process. And so I can say, what's the probability that I have 5 trees growing on a given acre of land, right? Because I can tell you statistics about how much happens on average, and then the Poisson random variable counts how many trees are in a acre or how many trees are in a square mile. I have to define what my interval is, and then the Poisson is how many times the thing happens in that interval. It could also be length. I could say, trying to think of an example, if I'm working on electrical lines and I could say, hey, there's an electrical fault every, how many electrical faults are there on 1,000 feet of electrical line, right? And so I can say, what's the probability? And so X is the number of electrical faults per 1,000 feet of electrical line. And then I can talk about questions like, what's the probability that I have 3 faults in 200 feet of electrical line, right? So it's how many times a thing happens on an interval if it follows a Poisson process. Okay, so that is the very top level general idea of what a negative binomial and a Poisson represents. Any questions about that before we get into the math and the code of how we calculate them? Oh man, I don't know what I said, but ticked Simon off so much he just left. I'm guessing that the network went down. Okay. So before we get into the code, the one last thing I wanted to say about this Poisson, and I kind of alluded to it right now, was that it is based on a parameter lambda. So in the same way when we talked about the normal distribution, every time we calculated something with the normal distribution, we had to tell our the mean and the standard deviation, because those were the 2 parameters that told me what kind of normal we had, right? Because we said, hey, one normal could look like this. One could look like this, except for the slanty thing. One might look like it's over here, right? And so I had to tell it what was the mean and what was the standard deviation, so it knew what my particular normal looked like. For the Poisson, that parameter is lambda. Lambda is the parameter that completely describes the Poisson distribution. And what lambda is, it's the expected value, right? So if I say if I say for MissionNet, if I say on average, MissionNet fails 3.5 times per hour, then 3.5 is the lambda for MissionNet on an interval of an hour, right? Because the number of failures in an hour is what I'm talking about. The average failures in an hour is 3.5. So that is the lambda for the Poisson distribution. What you guys need to be aware of, because this is the thing I see people miss a lot, is that you might have to adjust that lambda, right? So I use a dumb example of me sneezing down here at the bottom. If I tell you, hey, I sneeze an average of 3.5 times an hour, then my lambda is 3.5, but the lambda is 3.5 if I'm counting sneezes in an hour. If I then ask you, hey, what's the probability I sneeze 10 times in a day? That's a fine question, but now you've changed the interval from hours to day. So before I answer it, I have to change my lambda, and I have to say, well, if the average number of sneezes is 3.5 times an hour, then that means the average sneezes for a day is 84, because 3.5 times 24 is 84. So now I can answer the question, what is the probability that I sneeze 10 times in a day? I can now answer that knowing that the lambda for a day is 84, right? Same thing for that bottom one with the trees example, but understand that the lambda has to do with the interval. And if I give you the lambda for one interval, and then I ask a question for a different interval, you need to change the lambda for whatever the interval in question is. Any questions on how lambda works and why it is a Poisson random variable has to do for a specific interval, and we got to decide what that is?
What is so I understand the relationship between like I think it's mu and lambda, but what about I think it's called sigma squared and lambda?
Sure. So I can get into it a little deeper, but for a Poisson random, so for each one of these random variables, I just happen to be showing you because you don't need to calculate these things. You should just have them of, hey, based on this, if you know K and P, the expected value for this is K over P. The variance sigma squared, which is also the variance, is this thing because of the way it works out. It just turns out that for a Poisson random variable, the expected value and the variance are the same. There is some neat math to explain why that's true. I'm not as concerned that you understand why as much as I am that you be able to answer. If I gave you, some information like this, and then one of the questions was, hey, what is the variance of this Poisson random variable? That you should just know or be able to look up, well, the variance of a Poisson random variable is lambda. Lambda is this, therefore the variance is that number. So it just happens to be that for a Poisson random variable, the mu and the variance are both equal to lambda. So if you want to get deeper into the why, then set up in the eye. I'm happy to go through. But otherwise, all you need to know is, hey, isn't that cool that for a Poisson, they're both equal to the same thing? Does that answer your question?
So I think you might have explained it already, but I'm just like not understanding. But like, what? I guess like, never mind. I'll just come in for.
No, it's all right. Like talking about, like, I mean, I don't want to force you to sit here and explain it, but I've got the time to go. So is the question a larger question of trying to get at like, what is the meaning of these things that we've been putting on all of these, and why do we care?
I mean, I understand why those are the case, because like that seems like a more straightforward relation. It's just it seems weird to me that lambda is.
It is weird, and like, so the real short version of it is that I said it was like, hey, a quirky, funny thing. That's undercutting it. There's mathematical reasons for it, and without getting into the deeper reasons for it, the reason in a Poisson random variable that the mu and the variance are both equal to lambda comes to this idea that Poisson is what we call a memoryless function, meaning that what happened before I don't care about. Like for a geometric, if I say, what's the probability that I don't get my first success until my 8th try? And then if I say 9, I say, what's the probability that it's not to my 9th try? Well, 9th goes down because I've had more trials, right? Whereas a Poisson is just about a section of time. So when I say it happens in an hour, I don't care which hour it is, because what happened before doesn't matter. And so the distribution kind of moves along, and it's for a random interval. And as a result, the average and the standard deviation are related, because unlike some of the other distributions like a normal, where the mean tells me where it is, the mean kind of in a weird way is moving with this, and how spread out it is depends on the mean, because the mean is how often it's happening and the distribution is how spread out it is. Yeah, I'm not going to be able to give as good. If you're interested in it, let me know and I can kind of show you some cool pictures on there. But it comes to be, it's because of all the other ones we've described, it is a unique looking at a number of occurrences in an interval instead of counting a thing happening and not happening and becoming more and more unlikely. If that I know that doesn't get to it, but it is. You're not wrong to say it is odd and unlike the others we've looked at up to this point. Okay. The code for these, like the other ones, has the DP, Q, and R functions for each one of them. The thing to notice, though, is just like geometric was the weird one last time where we counted failures, the negative binomial is the weird one here, which makes sense because the negative binomial actually is the geometric function, if you look at this, is actually just a special case of the negative binomial, right? Because the negative binomial says how long does it take me to get my kth success, right? How long does it take me to get my fourth success or my fifth success? The geometric was just how long does it take to get my first success? So the geometric random variable is really just the negative binomial, but the special case where k equals 1, right? So it shouldn't be surprising that since R made us do geometric functions a little differently where we counted failures, that the negative binomial is going to make us do the same thing. And so we count failures as well. So in here, if I have a function dn binom, and let's talk about flipping a coin. And so if I say 2, 3, 0.5, so that's a D binom. So it means I am talking about a probability of an exact number. And so the way I read that function is it is saying, what is the probability that I get 2 failures before getting 3 successes? If every time the probability is 0.5. So in coin flipping speak, what that's saying is, what is the probability that it takes me 5 coin flips before I get my third head, okay? So using the terminology up here, if X is my negative binomial random variable, then this down here is saying, what is the probability that X equals 5 given that K equals 3, right? So it's that is the code for saying, what is the probability that I don't get my third success until my 5th trial? Or another way of saying it, it takes me 5 trials to get my third success. And so the way R does that is this D binom 2, 3 of saying, what is the probability that I got 2 failures before getting my third success? Which again could be a little confusing because the way we define it here, X is 5, and that doesn't actually show up here unless you add this up. 5 is the total number of trials it took, and the way R thinks of it is, yeah, that's what I said. It took you 2 failures before you got 3 successes. Any questions on that weirdness? All right, then let's look at some examples. So now we get to the part of, does anyone have an opinion of, would you prefer to go back and look at the last review question from Wednesday, or would you prefer to look at some of these problems? Or I can phrase it a different way. Is there, between these 3 problems and the that blue-eyed, brown-eyed question, which one would you guys like to see? I'll pick my favorite if you guys don't care. All right. Dealer's choice. So let's look at this. So are you guys seeing my R screen? Is anyone hearing me whatsoever? Is this just a,
Yes,
is this class? Oh, there we go. Okay, someone's got me. All right. Okay, so let's look at the review from last time. So this was a little bit of a multi-step question, so I thought it was a good one to go. I'm gonna just kind of go through it and stop me if you have questions. But if you don't, then that's totally fine. I'm going to use the 4-step problem solving on this again. And so the question, as it was asked, said, husband and wife both have brown eyes, but carry genes that make it possible for their children to have brown eyes with a probability of 75%, blue eyes with a probability of 1/8 or 12.5%, or green eyes with 12.5%. And then we asked two questions. One, what's the probability that the first blue-eyed child they have is their third child? And B, on average, how many children would such a pair of parents have before having a blue-eyed child? Now, a couple things about this that make this a unique but not difficult question. One, whenever we're talking about this before, we usually have success, failure, right? Heads or tails, something like that. Here we have three options: brown eyes, blue eyes, and green eyes. That doesn't matter though, because I can have more than one option as long as I decide, as long as I define what's success and what failure. And so in this case, we keep talking about the probability of getting blue-eyed children, right? So in this case, blue-eyed children are successes and anyone else is a failure, which as someone with hazel eyes, I find mildly insulting, but that is how we define it, right? So I have three options, but I don't actually care that I have brown and green, because brown and green together are just failure. Those are the ones I don't want. So I still have a success condition and a failure condition. Just happens that I have more things under the failure condition, right? And so using this 4-step, the first is going to be was to say it says define the random variable, right? So we're going to do that at line 23 here. And remember, defining the random variable is saying, what does the random variable represent? So in this case, X is the number of non-blue-eyed children the couple has before having a blue-eyed child. So this is a little different than we did it yesterday, because someone asked me, you know, usually we define it like the book and then we change it for ours. So someone said, hey, could we just define it as the number of failures? And I said, certainly. So I am doing this based on their request of saying, let's define it to count failures. And so I said that, hey, we're going to define it to count failures, okay? So we're going to say X is the number of non-blue-eyed children they have, or the number of failures, again, hurts my heart, before having a blue-eyed child. So that's what X is. And so then when we say, what kind of distribution is it? X is geometric because we're talking about counting until we get our first success, which by definition is a geometric. And we're going to say P, which is our probability of success, is 0.125 because blue eyes is success. Therefore, probability of success in this case is 0.125. Okay, then 3 says define the problem in mathematic terms, right? So we had two parts, an A and B. What's the probability that the first child they have, the first blue-eyed child is their third child, right? And that is because X is the number of failures before success, or the number of non-blue-eyed, then A is asking what's the probability that they have 2 failures before their first success, which would be probability that X equals 2, right? And then the second part says, on average, how many children would such a pair of parents have before having a blue-eyed child? So what we're saying is, what is the expected number of failures or non-blue-eyed children before they have that, which would be the expected value of X, right? Sometimes the question may not be a probability, maybe it's an expected value. Any questions on the setup in parts 1, 2, and 3 of this problem? Okay, so then 4 is just now solve it in code, right? So the first part is we're saying what's the probability that X equals 2, right? And like we said, in this case, we're counting failures So we're already speaking R's language. Because I want the probability that equals exactly 2, I'm going to use dgeom, right? When I'm talking about ranges, I usually use the pgeom function, but here I want to know the probability of getting an exact value of x, so I'm going to use dgeom. And so I'm going to say dgeom of 2, because in R speak, that means what's the probability that I have 2 failures before succeeding on my 3rd try. And so I put that in there, and I get down here. It looks like I get down as my answer here, 9.5%. So there is a 9.5% that their first blue-eyed child will be their 3rd child, right? For the expected value, I don't have to do any fancy code for that. For the expected value, all we are using is the fact that when you had this up, like Stephen was saying, that right here, this is a geometric, and so mu is the expected value, and so the expected value for a geometric random variable is 1 divided by the probability of success. Well, the probability of success here is 0.125, so 1 divided by 0.125 is 8. So this is saying that the expected value is 8, which answers our question. On average, we expect them to have 8 children, 8 non-blue-eyed children, before they have their first blue-eyed child. Okay, look at those steps, how the 4-step was set up, and how we answered each part, and how we did the code, and take 20 or 30 seconds, and then let me know if there's any parts of this that you would like re-explained, or if there's a part where you say, okay, I understand how that works, but I would have never come to that on my own. We can talk about where the disconnect is and what we can do about that. Okay. Hopefully that means we're feeling pretty good about doing something like this. And you guys have asked me before about on quizzes, and then maybe talking in the future about GRs, of saying, are we expected to do code, right? This, well, I don't expect you to do lab levels of blocks of code. This is the type of code that I might expect you to do on a quiz or GR, where I ask you a question and you just need to do a single line, right? That is not, I don't consider that as much code as I consider like doing a calculation on a calculator. It's easy as long as you know the conceptual part, which in this case is recognizing this is a geometric and how to use the dgeom function. So that's the type of line of function where I would feel happy to ask you that A-type question, and the real question is you deciding what kind of question it is, and then the easy part would be to put in that line dgeom so that you could then on the test give me the answer that it is 9.57%. Okay, so that's the type of thing that you guys should be prepared to be able to answer. All right, okay, so now let's jump over to use the time we have left to look at some binomial and Poisson type random variables. So here are some examples of the questions. So before we get into it, I want you guys to look at question 1 and 2 and tell me if you would be comfortable being able to at least define what kind of distribution you need, right? Because that is the biggest part. One of the lesson objectives is to say, hey, I'm going to give you a scenario. What random variable would you use? Because this is the last time I'm going to teach you new discrete, specifically named random variables. You have a total of 5 random variables to pick from now. You only have one continuous random variable, that is the normal distribution. And then I've given you 4 types of discrete random variable: geometric random variables, binomial random variables, negative binomial random variables and the Poisson random variable. So those are the only ones you're responsible for this block. So when I give a scenario and then say, hey, you got to figure out which distribution, it's not out of all distributions, it's out of these 5, right? So that's one of the main objectives. And really my main objective is that given a scenario like this, you can tell me that has to be this distribution. So the question is, looking at that first one, do you feel comfortable being able to at least pick out what is the distribution you would use? If you do not know, then now's the time to bring it up, because you should be able to, at this point, be able to tell me which of the, now maybe not off the top of your head, you might have to go back and look through and read these. You know, this is not a class and course about memorizing everything. Everything is open, but you should be able to go through and decide which one is the random variable you would use for this scenario. So think about that for a second, and then I'm going to ask somebody. All right, Preston, you won my lotto. You got a feeling or opinion or concrete idea on what distribution I would use for number 1?
No, sir. I do not. I apologize.
No, well, first of all, you guys got to stop apologizing. Like, there's a difference between being tactful and being like apologetic. Like, almost all of my messages and texts I get from you guys start like, sir, I'm sorry to ask for this, or I apologize. It's like, as long as you don't start the like text, hey, dirtbag, I'm going to miss class, deal with it, peace out. Like, that's a whole different question. But as long as you're just saying, hey, sir, I got a question, or sir, I'm going to miss class. You stop being like, unless you did something wrong. If you did something wrong, apologize. But to the best of my knowledge, you guys haven't done wrong stuff yet. So not having the answer is not an apologetic offense. It's just a something that we got to answer. So anyway, going back to that. So going to number 1, like I said, look at our options, right? And so here is I would look at that and say, so it says, so let me ask you, I'm going to stick with you, Preston, and keep you on the spot. So before we figure out what distribution is, and this is why we have the 4-step problem solving process, to try to think it out. So step 1 is saying define the random variable, which really means what is it that we are counting in here? What is the thing that we care about? So reading this question, could you at least give me an idea of what is the thing that we are counting, right? What is ultimately we're asking a question about probability. And so we're asking what's the probability that a thing is a certain number, which means we are counting a thing to see that it could be different numbers. So what is the thing in this scenario that we are counting?
It's the amount of successful made free throws.
Let's look at this. Well, it says right here that we are going to stay until we make 100 successful baskets, right? So the number of successful baskets we make is going to be 100. Does that make sense for the problem?
Yes, sir. Okay, so then it would just be the amount of shots. You're just counting the total number.
Right, and I say that seems like, oh, it's a minor difference, but it is kind of the key difference. Like, these are the things that I need you guys to look for and find in here, because a random variable, by definition, is something that could be different things, and we're trying to find the probability of it being different things. So in this situation, the number of baskets we make is set. The coach is not letting you leave until you make 100. So number of baskets equals 100. So therefore, it can't be a random variable. So the number of baskets we make can't be. But like Preston said, the number of shots it takes for us to make 100 could change. It could be anywhere from 100 if we just are awesome at free throws and we make 100 in a row, and so it only took us 100 shots to make 100 baskets. Or if we our shack, it could take us 200 to 300 shots before we make 100 baskets, right? So the number of shots it takes varies with random probability. And so that is our random variable. Okay, so that is the first kind of step of saying, what does our random variable count? And so in this case, if we make it X, because we use that letter a lot, X is equal to the number of shots we take. All right, so now we've decided what we're counting. So now we have to say what distribution, right? We said we only have 5 options, the 1 continuous and 4 discrete. So I'm going to just kind of go through my list here. Ryan, are you online?
Yes, sir.
Oh, I got 2 Ryans I forgot in this class. Dang. Okay, so we'll give let's start with Ryan Z. So Ryan, could this be a normal distribution? Is it possible that R is distributed normally?
Yes.
So let me ask you this. A normal distribution is continuous, which means it takes on any possible, it can take on any possible number in a range. So you're telling me it might take us 125.8327 shots?
No, because it's discrete.
Right. So, and that's why I'm putting this to you. So sometimes we don't need to get into the specifics of the random variables before we can throw them out as possibilities. We can just throw them out as saying, could it be normal? Normal is for a continuous random variable. Is this continuous? No, it is not a continuous random variable. We either make 100 shots or 101 or 102 or 103 and nowhere in between. So this can't be a normal distribution. Now, I will tell you, sometimes people talk about things and they'll say, hey, they'll talk about bell curve of class and things like that and say, hey, maybe the number of students is distributed normally. And in that case, they're really saying that it's estimated or it looks like it. But if we're talking about an actual distribution here, this can't be normal because the random variable is not continuous. So normal is out as an option. So now I've only got my 4 discrete options, and my options are geometric, binomial, and negative binomial, and Poisson, right? So the next question, so now I'll go down to Ryan Klein. So of those, what would be your first guess at what it might be? And when I say guess, what I mean is, what do you think it could be? And it doesn't mean you have to be right. It means we look at that and then we decide, does it meet all the criteria? And if not, we throw it out. So what would be your first best guess on what of those ones that we want here? We had geometric, binomial, negative binomial, and Poisson. And I'm happy to bring up any other slides if you want to look at it, or if you got your notes, you can look at those.
Yes, sir. I took pretty poor notes yesterday. Could you bring up the the slides from yesterday's too?
Okay, so here's when I say yesterday, I mean Wednesday. So here is the definition of geometric and binomial random variables.
Yeah, so I was thinking binomial.
Okay, so let's look at binomials. So the binomial in the binomial, I do a set number of trials, and then X represents how many successes I got. So does that apply to our situation here? A binomial says I have a set number of trials, and then I count how many times I succeed. Is that what happens here?
No, sir.
Oh, why? Why is it different?
Because you have to stay until you make the 100 baskets, so it's not a set number of shots, it's a continuous number of shots.
Well, so it's not, be careful with your words. I know what you mean, but not continuous. But what you're saying is the number of shots I make is variable, right?
Yes, sir.
So what is set?
That when you make 100 shots, you're done.
Right. So unlike the binomial, it's not binomial because binomial says set number of tries, variable, and we're counting the number of successes. But that's not what's happening here. What's happening here is we have a set number of successes and we are counting, our random variable is counting how many tries it takes. Does that jive with what this says? I'm still
Pardon?
shooting at you, Brian. Does that make sense?
Yes, sir, it does.
Okay, so here's our other two options. Which of these, if either, does it look like we might use?
Would it be the Poisson?
So Poisson says, I want to count how many times something happens in a given interval. So I agree. Are we counting in here how many times? So for it to be Poisson, X has to be counting how many times that things happen. So that means the number of times something happens is random within a set interval. Is that what's happening here?
No, sir. It's the negative binomial because it's
Okay, right. And so he's exactly right. It's a negative binomial, right? Because the negative binomial says that I have a set number of successes and I want to count how many times it takes to get that, right? Which is what we're doing. We have a set number of success. We don't get to leave until we make our 100th shot. And so the negative binomial is for when we want to count how many times it takes before we get a set number of successes. We want to count how many tries of shooting a basket we have to make until we get our 100th success, right? And so that was a little bit of a going back and forth, but I am glad we did it because that is exactly how this works. I do not expect any of you most of the time to just know it off of the first try, but you only have those 5 distributions. And so when you're presented with it, this is exactly what you should do. Make your best guess and then look at the explanation and go, is that really what I want? And if you convince yourself no, saying, oh, it's continuous. Okay, that can't be it. Then go back and go, well, then I think it's binomial. And then look at it and go, well, wait, here we have a set number of successes or trials. That's not where, okay, it can't be that one. And try the next one. We only have 5 to go through. Hopefully you get to it before your 5th try. But if it takes you to your 5th try, you still got it, right? So that, I am really glad we spent that time going through there because that is what the process is. Don't just take your first guess and go, that must be what it is. Go through and then check each of those boxes and say, is that what I want? Is that what I want? And then once you have it, now you've got it and move forward. We're at the end of our time, but I think that was a good use of it. I'm going to post this up after class. Here is that exact question and the 4-step process of answering it and doing it. So take a look at that. Feel comfortable with that. The next question is down there as well. And then next Tuesday is our review day. So between now and Tuesday, send me any questions that you have or you'd like to work through on this or anything we've talked to up in this point in class. And we will spend Tuesday working through those examples. All right, it is Friday and I'm standing between you and the weekend. So get out of here. Send me those questions so we can have a really great review on Tuesday. Otherwise, I will not see you until Tuesday. Do your best to enjoy the weekend if you can. Otherwise, I will do my best to make sure review is awesome so you can at least enjoy next weekend because it'll be after you ace the first GR. All right, I'll stick around for a couple of minutes if you got a question. Otherwise, I will see you guys on Tuesday.